this calm journey, you'll feel how we map over 1 billion stars with Gaia and how a galaxy becomes readable slowly. You don't need effort. Simply relax your jaw and let the room get quieter. Calm knowledge stays soft on purpose, so sleep can arrive naturally. Give it a little more than 2 hours and let the night do the work. Somewhere above the roof lines, the night is already moving, even when everything here feels still. If your day has been heavy, you do not have to carry it any further tonight. Let the room become simpler. Let your shoulders soften as if tension is gently unthreading itself. Let your breathing slow without effort, as if the air has all the time in the world. Inhale as though you are taking in quiet. Exhale as though you are setting down weight. Nothing needs to be solved right now. Begin with what is nearest. The familiar darkness behind closed eyes, the faint texture of distant sound, the steady sense of gravity holding you in place. It is patient and constant. It has been with you for your whole life, doing its work without asking for attention. Tonight you can notice it, not as pressure, but as reassurance. Now let the space above you feel less like a ceiling and more like a thin boundary between scales. The bed becomes a calm rectangle. The room becomes a quiet geometry of shadow and soft edges. Your home becomes a small island of warmth in a larger night. Outside lights do not need to be bright to be seen. They can be gentle. A few windows, a few street lamps, a few slow lines along roads. From above, a neighborhood looks like a small pattern of warmth, breathing without urgency. Higher still, the pattern widens. Roof lines gather into blocks. Blocks gather into a city. The city becomes a calm constellation of lamps and moving points, a living circuit that does not demand anything from you. It simply exists and continues, and slowly changes shape as the night deepens. And then, with more distance, the city becomes part of something round. From orbit, the night side of Earth is a tapestry of amber and gold, stitched along coasts and river valleys. Dark regions rest between the lights like quiet oceans. Along the edge of the planet, a thin atmospheric rim catches sunlight, a delicate line that looks almost too fragile to hold anything, and yet it holds everything you have ever known. Earth turns once every day, not in a hurry, not with effort, simply because it has always been turning. The sense of time becomes softer when you see it this way. Your concerns are still real and still yours, but they no longer fill the whole space. They become one small weather system inside a much larger sky. Stay with that for a moment. A sphere turning in silence, a thin line of air, a glow that marks where people live and sleep. Nothing here is asking you to perform. Nothing here is asking you to think quickly. Now let your attention drift outward again, beyond the moon's orbit, beyond the familiar planets, toward the faint boundary where the sun's outward breath begins to thin into interstellar space. The sun's influence does not end at a sharp edge. It fades. It becomes a gradient. Space is often like that, not walls, but transitions. In that transition, our solar system moves through a particular neighborhood of the Milky Way. Not the bright center and not the farthest rim, but a quieter lane in the disk, where stars are scattered widely enough that the night can still feel calm. We are not near the most crowded places. We are not near the most violent ones. We are in a region that has remained steady long enough for oceans to form. for chemistry to become biology, and for biology to become minds that wonder. The Milky Way is our home galaxy, a barred spiral. If you could see it from far away, it would appear as a broad disk with winding arms, a central bulge, and a long bar of stars crossing the core. From inside where we live, it is harder to read. Dust dims and hides. Lines of sight overlap. Near and far blend together. Mapping it is like trying to understand a whole landscape while standing deep inside it, with only narrow windows between the trees. And yet, over time, the galaxy has made itself knowable. There are stars of many ages here. Some are young, hot, bright, and short-lived. Some are small, faint, and extremely long-lived. Red dwarfs that can endure for tens of billions of years. There are star-forming regions where cold molecular clouds collapse under gravity. There are ancient globular clusters, dense swarms of hundreds of thousands of stars bound tightly together, relics from the galaxy's early history. There are supernova remnants, expanding like lace into the space between stars, and there are quiet regions where very little changes for millions of years at a time. If you could sense the galaxy in different kinds of light at once, it would feel like layered realities sharing the same space. In visible light, you would see starlight and dark lanes of dust. In infrared light, you would see through much of that dust into warmer regions and the glow of star-forming clouds. In radio light, you would trace vast reservoirs of hydrogen, including the famous 21-centimeter emission line from neutral hydrogen atoms, a whisper that has helped astronomers map the rotation of the galaxy and the distribution of gas. In X-rays, you would see hot plasma in supernova remnants and energetic environments near compact objects, places where gravity and motion heat matter to millions of degrees. You do not need to hold every wavelength in your mind. You only need the feeling of it. The idea that the same galaxy can look different depending on how you listen to its light. Our sun orbits the galactic center at roughly 220 kilometers per second. One full orbit takes on the order of 225 to 250 million years. That span is sometimes called a galactic year. It is such a long time that Earth has completed only about 20 of these orbits since the solar system formed. When the first dinosaurs appeared, we were in a different sector of the Milky Way. When the first mammals began to diversify, the background of nearby stars was not exactly what it is now. The sky feels fixed because our lives are short. The galaxy is always in motion, quietly, patiently, continuously. And as the sun travels, it does not follow a perfect circle, and it does not stay perfectly in the midplane of the disk. It also drifts above and below the plane in a slow oscillation, like a gentle bobbing that takes tens of millions of years. The Milky Way itself is not perfectly flat either. Its outer disk is warped and twisted, as though a subtle gravitational hand has pressed on it from one side. Interactions with satellite galaxies, infalling gas, and the uneven shape of the dark matter halo may all contribute to that warp. This can sound complicated, but you can let it remain simple tonight. A spiral that turns, a disk that is slightly bent, a star that follows a long, steady path. Dark matter is one of the main reasons the Milky Way can hold itself together. If you only counted the mass we can see, the stars and gas and dust, the galaxy would not have enough gravity to keep its outer regions rotating as fast as they do. Stars in the outer disk move too quickly for the visible mass alone to bind them. The simplest explanation is that there is additional mass we cannot see, a halo extending far beyond the luminous disk. It does not shine, it does not emit or absorb light in any ordinary way, but its gravity is real, and it shapes the structure of the galaxy like a hidden scaffold. You can hold that idea lightly, an unseen framework known by its effects. You do not need to force your mind to grasp it fully tonight. It is enough to let it sit in the background like an ocean current you cannot see, but can feel in the slow movement of the surface. In the center of the Milky Way, there is a different kind of gravity. Buried behind dense clouds of dust lies Sagittarius, a star, a supermassive black hole with a mass of about 4 million suns. It does not glow by itself. What we see is the matter around it, heated and accelerated, sometimes flaring as gas falls inward. Stars close to the center move at thousands of kilometers per second, tracing tight orbits that reveal the black hole's presence with remarkable clarity. There is something quietly astonishing about that. A mind made of cells and salt water can watch starlight, measure motion, and infer the presence of a gravitational abyss at the heart of a galaxy. Not through drama, but through patience, through repeated observation, through careful comparisons that slowly reduce uncertainty. The Milky Way is more than its center, though. It is a system with a long memory, and that memory includes collisions. Our galaxy has grown by accreting smaller galaxies over billions of years. Some were absorbed so long ago that only chemical traces remain in the stars. Others are still being pulled apart right now, leaving long stellar streams that wrap around the Milky Way like faint tidal scars. One of the most famous ongoing examples is the Sagittarius dwarf galaxy. It is being disrupted as it orbits the Milky Way. Its stars are stretched into elongated ribbons that arc across the sky. By tracing these streams, astronomers can reconstruct past encounters and also probe the shape of the dark matter halo that guided the disruption. You do not need to picture this as violence. In space, even disruption can be slow. The distances between stars are immense. What changes is the gravitational landscape, and that change unfolds over long spans of time, like geology rather than catastrophe. And in the far future, there is another collision written into the motions of our local neighborhood. Andromeda, the nearest large spiral galaxy, is about 2.5 million light years away. It is approaching at roughly 110 kilometers per second. That seems fast in human terms, but in cosmic time, it is a slow drift. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to begin a long interaction that ends in a merger, passing through each other, distorting each other, and eventually settling into a single larger galaxy, likely more elliptical in shape than either is today. For individual stars, this is mostly gentle. Direct collisions between stars are exceedingly rare. The main change is in orbits, paths reshape, the sky transforms over deep time, the solar system, if it still exists in anything like its current form, would likely survive but may be carried into a different route through the merged galaxy. If you let your imagination rest on that, it can feel both unsettling and strangely calming. Unsettling, because it reminds you that stability is not permanent. Calming, because it shows the change on this scale is slow, gradual, and lawful. The universe does not rush, it unfolds. And if you've been drifting with this story, you may notice something else. The mind can hold vast ideas without becoming tense, as long as the pace is gentle and the language stays soft. It is not the topic that keeps people awake. It is the pressure. Remove the pressure, and even black holes can become part of a lullaby. So we keep the pressure low. We let the galaxy become a place you move through, rather than a puzzle you must solve. And from here we can drift closer again, to something less famous, less dramatic, but quietly relevant, because it is the interstellar environment surrounding us right now. The solar system is not traveling through a perfectly uniform medium. It moves through structure, cavities, clouds, magnetic fields, subtle variations in density and temperature. These are details you rarely think about, but they are part of the texture of the galaxy, like wind patterns are part of the texture of Earth. Around our neighborhood lies a region often called the local bubble, a low-density cavity in the interstellar medium, roughly on the order of 1,000 light-years across. It is not empty. It is thinner, more rarefied, and warmer than the denser clouds around it. Many astronomers think this cavity was carved by multiple supernova explosions over the past 10 to 20 million years. Their shock waves, overlapping, sweeping gas and dust outward, leaving behind a kind of hollow. The sun did not form inside this bubble. It formed elsewhere in the disk, and over time it moved into this region as it orbited the Milky Way. Right now we sit near one side of the cavity, like a small boat near the edge of a wide, shallow bay. The edges of the local bubble are not walls. They are hazy boundaries made of cooler, denser clouds. One such cloud is the local interstellar cloud, a partially ionized region that the solar system is passing through. Beyond it lie other clouds with different pressures and different magnetic field orientations. Over long spans of time, the solar system will encounter these regions in sequence. And these surroundings matter because the sun is not only a source of light, it is also a source of plasma. The solar wind, a constant outflow of charged particles, expands outward and creates a bubble in interstellar space called the heliosphere. Where the solar wind meets the interstellar medium, the flow slows and bends, forming a complex frontier that partially reduces the amount of galactic cosmic rays that reach the inner solar system. If the external conditions change, the heliosphere can change too, subtly adjusting its size and shape. On human timescales, these shifts are too slow to feel. On geological timescales, they might modulate the background environment in ways we are still trying to understand. It is a reminder that even in what feels like empty space, the galaxy has weather. Not clouds and rain, but fields, flows, and gradients. Not storms you can hear, but structures you can measure. If you've been listening for a while, you might be close to sleep now. If so, you do not need to hold every detail. Let the facts become a soft outline, and let the imagery do the work. A thin atmospheric rim, a spiral turning, a cavity of warm, rarefied gas, a drifting star carrying a small system of worlds. And as we continue from this local neighborhood, we can begin to follow a different thread, not only where we are, but how we know. The instruments that read invisible wavelengths, the surveys that measure stellar motion with exquisite precision, the simulations that rewind time, the slow assembly of a map that is never finished, only refined. So, staying gentle, we will let our attention glide outward again, not in a rush, but with the same calm pace, toward the tools and clues that allow us to trace the Milky Way's hidden structure, and beyond that, toward the deeper question of how a galaxy like ours emerged from an early universe that was once hotter, denser, and almost unimaginably new. And from here we can continue in the same gentle way, following that thread of how we know what we know, while also letting the Milky Way's past begin to reveal itself not as a list of events, but as a slow layering of time. When you look at the night sky, it is easy to feel as if everything has always been in its place. But the Milky Way did not arrive fully formed. It assembled, it grew, it changed shape, it kept what it could hold, and it let other things drift away. Over billions of years, the galaxy became what it is now through a long series of quiet additions and occasional disruptions, like a shoreline that slowly changes after each tide. A galaxy is not only stars, it is also memory, and much of that memory is written in the stars that live far from the bright disk, in a dim, extended region called the halo. The halo is not a solid shell. It is a sparse population of ancient stars, globular clusters, and long, faint streams that arc around the galaxy. Compared to the luminous disk, the halo is almost empty, but it matters because it holds clues from an earlier time. Some of the oldest objects in the Milky Way are globular clusters, compact spheres containing hundreds of thousands, sometimes millions of stars. Many of them are more than 12 billion years old. They formed when the universe was young, when the first generations of stars were still enriching the cosmos with heavier elements. In their chemistry, you can see the early universe's simplicity. In their orbits, you can see how the Milky Way's gravity has held them for an almost unimaginable span of time. The halo also contains stars that do not seem to belong to the galaxy's calm rotation. Many move on tilted or elongated paths, rising far above the disk and then diving back through it. These are not the neat circular motions you would expect from a stable spiral system. They are the signatures of a more chaotic past, when smaller galaxies fell in and were pulled apart. This is one of the most important ideas to hold lightly without tension. The Milky Way is partly built from other galaxies. Over cosmic time, our galaxy has absorbed many smaller companions. Some were swallowed so long ago that only a faint chemical trace remains. Others are still in the process of being disrupted right now. When a small galaxy drifts too close, the Milky Way's tidal forces stretch it. Its stars begin to spill out along its orbit, forming a stellar stream, a long ribbon that wraps around the galaxy like a pale thread. One of the most famous ongoing examples is the Sagittarius dwarf galaxy. It is being torn apart as it orbits the Milky Way, leaving behind streams that loop around the disk. These streams are not only remnants of a disrupted system, they are also tools. Their shapes and motions respond to the galaxy's gravitational field. By mapping them, astronomers can infer the distribution of mass that is otherwise invisible. And that brings us back to the quiet presence beneath everything, the dark matter halo. The visible Milky Way, the part made of stars and glowing gas, sits inside a much larger structure of dark matter. This halo extends far beyond the bright disk, likely reaching hundreds of thousands of light years from the center. It does not shine, but it holds. It is the hidden weight that keeps the galaxy bound. When astronomers measure how fast stars and gas move at different distances from the center, they find that the outer regions remain too fast to be held by visible matter alone. The simplest explanation is that there is far more mass than we can see, and most of it is dark. If you let that idea settle, it can feel strangely soothing. Not because it is simple, but because it is consistent. The unseen can still be known through its effects. You do not need to see the wind to know the wind is there. You only need to watch how the trees move. In the same way, the halo's shape can be inferred by watching how streams curve, how satellite galaxies orbit, and how stars in the far outskirts move. The halo may not be perfectly spherical. It may be slightly stretched or gently distorted, especially by the pull of massive companions like the Large Magellanic Cloud. Even the dark scaffolding can shift under the influence of other mass. The Milky Way is not a rigid object. It is a living gravitational structure, always responding. And once you start thinking in those terms, the galaxy becomes less like a fixed picture and more like a slow choreography. There is evidence that one of the most significant mergers in the Milky Way's history involved a system often referred to as Gaia Enceladus. The details are still being refined, but the outline is clear. Long ago, a substantial dwarf galaxy merged with the Milky Way, leaving behind a population of stars that now occupy the halo and contribute to the thick disk. These stars share patterns in their chemistry and motion that hint at a common origin. They are like a family of travelers who entered the same city at the same time and never fully blended into the local rhythm. The remarkable part is not only that such events happened, but that we can still detect them. This is where the story of formation becomes gentle again, because it is not guesswork. It is measurement, repeated and cross-checked. Surveys of stellar positions and motions allow astronomers to identify groups of stars moving together or stars that share chemical fingerprints, suggesting they formed in the same environment. In that way, the Milky Way can be read like a layered archive, not a single narrative line, but overlapping chapters. And if you are listening in a sleepy way, you do not need to hold every chapter at once. It is enough to feel the shape of it, a galaxy that grew through accretion, that carries scars in the form of streams, and that keeps ancient relics in globular clusters and halo stars. Now, there is a common instinct to imagine mergers as violent, loud events. But in space, even collisions can be slow. When galaxies merge, the stars almost never collide directly. The distances between stars are vast. What changes is the gravitational field. Orbits stretch and reshape. Gas clouds compress and trigger bursts of star formation. Over long spans of time, the distinct structures blur into a new form. The drama is real, but it unfolds on timescales so long that it can feel like geology rather than catastrophe. This matters for the Milky Way's future too, because the Milky Way is not alone. It is part of the local group, and the largest neighbor in that group is the Andromeda Galaxy. Andromeda is approaching at roughly 110 kilometers per second, and in about 4 to 5 billion years, the two galaxies are expected to begin a long interaction that ends in a merger. You do not need to imagine this as a sudden event. It is more like a slow tide pulling two immense spirals toward one another. Over billions of years, their shapes will distort, their disks will warp, long tails of stars and gas will be drawn out. They will pass through each other more than once, and eventually they will settle into a single, larger system, probably more elliptical in shape than either is today. For the solar system, if it still exists in anything like its current form, the most likely outcome is not destruction but relocation. Our orbit around the galactic center may shift. The night sky over deep time would be rewritten, but the planets would continue to circle the sun, and the sun would continue its own slow evolution. Even when the galaxy changes, the local rhythm of a star system can remain steady. There is a calm lesson hidden inside that, and it does not need to be stated strongly. Change does not always mean collapse. Sometimes change is simply reorganization. And still, while mergers and halo streams tell us how the Milky Way grew, there is another part of the story that is closer, quieter, and more continuous: the disk itself. The disk is where most of the Milky Way's stars live. It is where new stars are born from cold molecular clouds. It is where the interstellar medium, the mixture of gas and dust between the stars, cycles through phases, dense clouds, glowing regions of ionized hydrogen, diffuse warm gas, and hot plasma stirred by supernovae. The disk is not a flat sheet of light. It is layered and textured with spiral arms, spurs, gaps, and a central bar shaping how material moves. And because we live inside the disk, this is also the part of the galaxy that is hardest to see in a simple way. Dust hides many regions in visible light. Lines of sight overlap. Near and far can blur together. The Milky Way is like a landscape you are walking through at night with a lantern. You can see nearby details clearly, but the full shape requires different kinds of light. That is why the next step in this journey will feel different and still calm. We have traced the Milky Way's past through the halo, through globular clusters, stellar streams, and the lingering signatures of ancient mergers. Now we can drift inward again, toward the disk's living structure, toward the gas and dust that make star formation possible, toward the energy that sometimes rises above the plane in vast outflows, and toward the faint, extended envelope of hot gas that surrounds the galaxy. We will not rush into detail. We will let it unfold the way the galaxy itself unfolds, slowly, layer by layer, wavelength by wavelength, as if we are learning to see in the dark without straining our eyes. So, gently we continue. From the halo's quiet threads we move toward the breathing of the disk, the space between stars, and the large structures that become visible when we look beyond ordinary light. They are more like long-lived traffic patterns in a rotating flow. Stars do not stay neatly inside an arm forever, and the arm itself is not a solid ridge you could touch. It is a region where material tends to gather, where gas is nudged into denser states, and where the cycle of birth becomes easier to begin. When gas is compressed inside these patterns, it cools. Cooling allows it to clump. Clumping allows gravity to take hold. And once gravity wins over pressure, a cloud begins to collapse, slowly at first, then faster, until parts of it become dense enough to ignite new stars. In the Milky Way, many of these nurseries hide behind dust. Dust grains are small, but they are effective at blocking visible light. So the most active star-forming regions can look like darkness in a telescope that only sees the optical sky. Yet in infrared, that darkness becomes luminous. Warm dust glows. Embedded protostars reveal themselves, and the structure of the cloud looks less like an empty patch and more like a folded landscape. Inside a molecular cloud, star formation is not gentle in the emotional sense, but it can still be imagined as quiet in motion. Cold gas collects into filaments. Dense knots form along those filaments. Some knots become cores. Some cores become protostars. Around each newborn star, material spirals inward through a disk, and inside those disks, planets may eventually assemble grain by grain, orbit by orbit, over millions of years. Not all stars are born equal. Many are born small, like red dwarfs, which can shine for tens of billions of years. Some are born massive, bright, and short-lived. The most massive stars can exhaust their fuel in only a few million years. They flood their surroundings with ultraviolet light, carving cavities in the gas and driving winds that push material outward. They do not simply appear and then fade. They reshape the medium around them, and in doing so, they influence what can form next. This is one reason the disk feels alive. It is a system with feedback. When a massive star ends its life, the ending is a supernova. A single supernova releases around 1044 joules of energy, about 10 51 ergs, in a burst that can briefly outshine an entire galaxy in some wavelengths. The shock wave expands into the interstellar medium, heating gas to millions of degrees, accelerating cosmic rays, and sweeping up shells of material that can stretch for dozens of light years. Over time, many such explosions overlap. They can create superbubbles, large cavities of hot rarefied gas, bordered by cooler, denser shells, where new clouds may be compressed and new stars may form. So the disk is not only a place where stars are made, it is also a place where stars continually rework the conditions for future stars. If you hold this gently, it can become soothing rather than noisy. A slow recycling, a circulation. Gas cools into clouds. Clouds form stars. Stars return energy and enriched material. The medium shifts again, and the pattern continues with no urgency, just persistence. In the language of astronomy, the Milky Way contains a thin disk and a thick disk. The thin disk is where most of the cold gas lives and where most current star formation occurs. Its scale height is only a few hundred parsecs, on the order of 1,000 light years. The thick disk extends farther above and below the plane, with older stars and generally lower metallicity. Its stars have orbits that are more stirred, less confined, as if the early Milky Way was a rougher place, or as if past mergers and perturbations left the disk warmer in its motions. Even the geometry is not perfectly flat. The outer disk is warped. The warp is subtle but real, and it suggests that the Milky Way is still responding to infalling gas and to the gravitational pull of companions. It is stable enough to feel like home, but it is not static. Near the center, the disk meets the bar and the bulge. The bar is a long structure of stars crossing the inner region, and it helps channel gas inward. Where gas flows inward, conditions change. Densities rise. Turbulence grows. Magnetic fields twist. Star formation can become more intense in some zones, while in others, powerful feedback and shear can keep gas from settling easily. And above and below the inner disk, there are signs of something even larger, not just local cavities, but vast outflows. One of the most striking examples is the pair of structures known as the Fermi bubbles. They are enormous lobes extending tens of thousands of light years above and below the galactic plane, discovered in gamma rays. Their edges are relatively sharp, their interiors are filled with high-energy particles, and their symmetry around the center suggests an origin tied to the inner Milky Way. There are two broad categories of explanation that astronomers take seriously. One is that the bubbles were inflated by a past active episode of Sagittarius A, when the central black hole accreted more material than it does today and released energy into the surrounding medium. Another is that they were produced by intense star formation near the center, where clusters of massive stars and frequent supernovae could drive a sustained galactic wind. Both scenarios involve large-scale feedback, and both connect the quiet present to a more active past. What matters for our calm drift tonight is not which explanation you prefer, but the sense of scale. The Milky Way is not only rotating and forming stars, it can also breathe. Energy can flow from the dense inner regions outward into the halo, carrying heat and particles far above the disk. This leads naturally to the idea of a galactic fountain. In a fountain, gas is heated and driven upward from the disk, rising into the halo, cooling over time, and eventually raining back down. Observations of high-velocity clouds, along with absorption studies of gas in the halo, suggest that some form of this circulation happens. It is not a single, simple jet. It is a distributed, multi-scale exchange between disk and halo. And if the halo is involved in this circulation, then the story extends beyond what we see as the bright disk at all. There is a larger envelope of gas around the Milky Way called the circumgalactic medium, often shortened to CGM. It is tenuous, hot, and difficult to observe directly, but it may contain a significant fraction of the galaxy's ordinary matter. In some estimates, the CGM around large galaxies could hold as much baryonic mass as the stars in the disk itself. Much of this gas may be at temperatures of 1,000,000 Kelvin or more, forming a hot corona that extends far beyond the visible edge. This matters because of an old puzzle. When cosmologists measure the total amount of ordinary matter in the universe based on early universe physics and observations of the cosmic microwave background, they get a specific value for the cosmic baryon fraction. But when astronomers count the baryons in stars and cold gas inside galaxies, many baryons appear to be missing. A large portion may be hiding in hot, diffuse reservoirs like the CGM and the intergalactic medium. In the Milky Way, the evidence for this hot halo comes from several directions. X-ray observations reveal diffuse emission that can be explained by hot plasma, ultraviolet absorption lines, seen when we look at distant background sources, show signatures of highly ionized oxygen and other elements that trace warm, hot gas. The details are complex, but the message is steady. Our galaxy is surrounded by an extended atmosphere that is faint, hot, and massive. If you want an image that stays calm, you can imagine the Milky Way not as a sharp-edged island of stars, but as a luminous disk embedded in a much larger dim halo of gas and dark matter. The stars are the bright part you notice first. The gas is the part that carries the ongoing chemistry. The dark matter is the framework you infer by its pull, and all of it sits inside an even broader web of cosmic structure. Inside the disk itself, there is another subtle layer that shapes everything: magnetism. The magnetic field of the Milky Way is weak in everyday units, on the order of micro-Gauss, far weaker than the field near a refrigerator magnet, But across tens of thousands of light years, even a weak field can matter. It guides charged particles. It influences how gas clouds move and fragment. It helps shape the propagation of cosmic rays. It can add a kind of tension to the interstellar medium, not visible to the eye but real in its effects. Astronomers study galactic magnetic fields using polarization of radio emission, Faraday rotation of signals passing through ionized gas, and the alignment of dust grains that polarize starlight. These methods are delicate. They rely on reading slight twists in light and radio waves, but over time they have revealed that the Milky Way's magnetic field has structure. It follows spiral patterns in the disk, with reversals and complex geometry that we are still mapping. Cosmic rays also belong to this story. They are high-energy particles, mostly protons, and heavier nuclei, accelerated by shock waves and other energetic processes. They diffuse through the galaxy, guided by magnetic fields, colliding with gas, producing gamma rays, and carrying energy across large distances. Cosmic rays are part of the disk's invisible activity, a background shimmer of energetic motion that does not need to be felt to be real. If you notice your mind tensing when energy is mentioned, you can let it soften again by returning to the pace. These are not rapid events in your room. These are slow, distributed processes across a galaxy. They can be known without being urgent. Now, there is one more place in the disk that quietly matters to the shape of the Milky Way, the region where cold gas meets the long-term gravitational structure. Spiral structure, the central bar, the distribution of mass in the disk and halo, and the ongoing infall of gas from outside all interact. Gas can flow inward along the bar. Gas can be compressed in spiral density waves. Gas can be lifted into the halo by feedback and then cool and return. And fresh gas can be accreted from the surroundings, feeding new generations of star formation. This is one reason the Milky Way is not finished. It is old, but not complete. Galaxies are not built once. They are assembled, adjusted, and maintained over billions of years. If you zoom in toward the disk again, you find an even finer texture. Dust lanes, filaments, shells, cavities, and regions of ionized gas glowing faintly around clusters of young stars. Some of these glowing regions are called HR2 regions, where ultraviolet light from hot stars strips electrons from hydrogen atoms, making the gas luminous in characteristic lines. These are the bright signs of recent star formation, and they appear as nebulous patches in images of the Milky Way, sometimes delicate and lace-like, sometimes dense and bright. There are also quieter clouds, colder, darker, where starlight does not easily penetrate. Inside them, chemistry continues slowly. Simple molecules form, more complex molecules can form, and within the densest cores, the next generation of stars begins its long, hidden approach toward ignition. This is the kind of content that can be heavy if it is delivered like a lecture. But it becomes lighter when you treat it as scenery rather than a test. You do not need to memorize these categories tonight. You can let them pass like distant landscapes seen from a moving train. A disk with spiral patterns, clouds that cool, stars that form and shine, explosions that return material, hot gas that rises and falls, a faint extended halo of warm and hot plasma, a magnetic weave, a slow circulation. And inside all of this, our own neighborhood is not special in brightness, but it is special in what it allows: stability. We are not in the central starburst regions. We are not close to the densest clustering of massive stars. We are in a part of the disk where conditions have been calm enough for long enough for complex chemistry and long histories to unfold. That does not mean the environment is perfectly quiet. It means the extremes are less frequent and the intervals of relative calm are long. Even within the disk, there are variations. Some regions are crowded with young clusters and active nebulae. Some regions are comparatively sparse. Between the arms, the interarm zones can be quieter in terms of star formation, with older stars and less dense gas. The Sun's orbit carries it in and out of these different zones over cosmic time. If you imagine the Milky Way as a spiral river of stars, our solar system is like a small, drifting raft moving along the flow, sometimes passing near brighter, more active banks, sometimes moving through wider, quieter stretches. The raft does not need to know the full map to keep drifting, and neither do you tonight. The shape of the disk, the pattern of gas, and the traces of feedback also connect to another kind of mapping, the attempt to reconstruct a three-dimensional picture from inside. Because we live inside the Milky Way, many of the structures we talk about are inferred rather than directly seen as a whole. Dust obscures the plane. Distances are difficult. Overlapping features confuse simple interpretation. So astronomers combine many tools: radio surveys of hydrogen, infrared maps of dust and stars, measurements of stellar motion, and models that test which structures can produce the patterns we observe. In the disk, velocity becomes a clue. Gas moving toward or away from us shifts its spectral lines. Stars move with characteristic patterns depending on whether they belong to the thin disk, thick disk, bar, bulge, or halo. Clusters carry shared ages and chemical fingerprints. And streams of stars reveal prior disruptions. The Milky Way is not read from one image. It is read from many layers of evidence assembled patiently. If you notice how this feels, it can be calming in itself. A slow assembly, a map that is refined rather than finished, an understanding that deepens without needing to rush. Now, holding all of this together, we can let our attention return to a smaller scale, not to repeat what you already heard, but to prepare the next step in a way that stays smooth. We have drifted through the disk as a living medium. We have touched on the way stars form, the way explosions shape cavities, the way energy can rise into the halo, and the way a faint circumgalactic atmosphere surrounds the visible galaxy. And we have seen that even the grand structures, like the Fermi bubbles, are part of the same larger process, a galaxy that can cycle material and energy across enormous distances. From here, the natural continuation is not to jump suddenly to a new subject, but to slide into a particular region of the disk that is both ordinary and intimate. The spiral neighborhood that includes our sun, the local arrangement of arms and interarm space, the pattern of star formation nearby, and the gentle path our system follows through it all. Because when you come back from superclusters of ideas, the next calm move is to rest again on a familiar lane of the Milky Way, and to notice how the grand processes we have described still leave small, quiet signatures right where we are. Now, staying with that wider picture of the Milky Way's disk, its faint outer gas, and the slow exchange between the galaxy and the space around it, we can let our attention narrow again, not by cutting away, but by drifting inward gently, until the scale feels personal. Because the Milky Way is not only a grand structure of arms and halos, it is also a neighborhood. And we are moving through one small, specific region of it right now, carried along by the galaxy's rotation, with a steadiness so constant that it can feel like stillness. From far away, spiral arms look like clear ribbons. From inside the disk, they are less like painted lines and more like broad zones, regions where gas is slightly denser, where gravity gathers material a little more strongly, where cold clouds are more likely to collapse into new stars. Spiral arms are not fixed walls. They are patterns that move through the disk, and the stars move through them too, each one following its own orbit, each one keeping its own time. Our sun is not in the crowded central bulge, and not out at the thin, dim edge. It sits in the disk, at a distance of roughly 26,000 light-years from the galactic center, in a region that is sometimes called the Orion Arm, or the local arm. It is not one of the Milky Way's largest arms. It is more like a spur, a bridge of star-forming material between larger structures, often described as lying between the Sagittarius Arm and the Perseus Arm. Even that simple statement carries a quiet comfort if you let it. Between, not at the center, not at the rim. Between, in a lane where stars are separated by wide distances, where the night can be dark enough to be calm, where the galaxy has had enough time to settle into long rhythms. If you imagine the Milky Way as a vast turning disk, then imagine a small, bright bead moving within it, the sun. Around that bead, a thin cloud of worlds. One of them is Earth, and around Earth tonight, a room that can feel heavy or light, depending on what your mind is holding. The scales nest inside one another without effort. You do not have to climb them. You can simply notice that they exist. The local arm is not empty. It contains star-forming regions that have shaped our sky, even if most people do not think of them as part of the same structure. The Orion molecular cloud complex, for example, is a broad collection of gas and dust, where new stars are still forming, and within it lies the Orion Nebula, a bright nursery of young stars. Nearby are other regions like Taurus, where cold clouds create stars more quietly, and Scorpius Centaurus, a loose association of young, massive stars that has influenced the interstellar environment around us. These regions are connected by something subtle, the interstellar medium, the thin mixture of gas and dust that fills the space between stars. It is thin by any everyday standard, and yet it is not nothing. It has structure. It has temperature. It has density variations. It has magnetic fields. It has motions that can be slow and laminar in one place and turbulent and stirred in another. If Earth has weather in air and water, the Milky Way has weather in gas and plasma and fields, and the sun is traveling through that weather. When you hear the word space, you might imagine emptiness. But our region is threaded with faint material. There are warmer, more diffuse areas and cooler, denser clouds. There are boundaries that are not sharp, more like gradients where one kind of medium blends into another. There are pockets carved out by ancient violence, and pockets still dense enough to birth new stars. One of the most important of these local structures is the local bubble, a low-density cavity in the interstellar medium, roughly on the order of 1,000 light-years across. It is not a perfect sphere. It is irregular, shaped by overlapping shock waves from multiple supernova explosions that likely occurred over the last 10 to 20 million years. Massive stars lived quickly, burned through their fuel, and ended in explosions that pushed surrounding gas outward. Over time, the expanding fronts overlapped, sweeping away much of the cooler gas and dust, and leaving a region filled with hotter, more rarefied material. It can help to imagine it not as a void, but as a gentle hollow, like a bay where the water is calmer because the wind has a different path. We sit near one side of this cavity, not centered within it, moving along with the sun as it orbits the galaxy. And within that broad cavity, there are smaller clouds. The solar system is currently passing through a region often called the local interstellar cloud, a partially ionized mix of gas that is cooler and denser than the hotter interior of the local bubble, but still extremely tenuous compared to anything on Earth. Beyond it lie other clouds with different properties, and over long times, the sun will pass from one to another, not with a dramatic boundary crossing, but with slow changes in the background. These changes matter because the sun does not only give light, it also sends out a steady flow of charged particles called the solar wind. That wind expands outward and creates a protective region around the solar system, the heliosphere, a kind of bubble shaped by the balance between the outward pressure of the solar wind and the inward pressure of the interstellar medium. Where the solar wind meets the surrounding medium, it slows, bends, and forms boundaries that are complex and layered. Most of this is quiet, invisible, and far away, but it has a consequence. It helps modulate the flux of some galactic cosmic rays that reach the inner solar system. If the environment outside changes, the heliosphere's shape and size can change as well, subtly altering how much high-energy radiation filters inward. On human timescales, none of this is something you feel. It unfolds too slowly. But on geological timescales, it becomes part of the background that Earth's history is written on top of. The Earth is not isolated. It is a small world moving through a galaxy that has texture. If you let yourself stay calm with that, it does not have to be unsettling. It can be grounding in a strange way, because it suggests that your life too is moving through environments. Some are dense with pressure, some are thin and spacious, some are shaped by past events that you never witnessed, and yet you keep moving, quietly, continuously, the way the sun keeps moving. The sun's orbit around the Milky Way is often described with a single speed, about 220 kilometers per second relative to the galactic center. It is a useful number, but the truth is more subtle. The sun's path is not a perfect circle. It is slightly elliptical, and it is influenced by the distribution of mass in the disk and the central bar. Over long time, its orbit can shift gently inward or outward as it exchanges angular momentum with patterns in the disk, including spiral structure. There is also another motion, one that people find oddly soothing once they picture it. The sun does not remain exactly in the midplane of the disk. It oscillates above and below that plane in a slow vertical motion, like a gentle bobbing that takes tens of millions of years to complete. Estimates vary, but the sun may cross the midplane roughly every 30 million years or so, completing a full up and down cycle in something like 60 million years. The disk itself is not perfectly flat either. It is warped and twisted in its outer regions, likely due to interactions with satellite galaxies and infalling gas, and perhaps shaped by the uneven form of the dark matter halo. So the sun's vertical motion is not just a simple wave in a flat sheet. It is a motion through a living, slightly bent structure. These are long times. They are so long that the mind cannot hold them the way it holds a day. But you do not need to hold them. You can let them be like a tide, something you know is moving even if you cannot watch it happen. Over those long timescales, the sun also passes through spiral features. Here, it is important to be gentle with certainty. Spiral structure is complicated, and the Milky Way's arms are not all mapped with perfect agreement because we are inside the disk and dust obscures our view in visible light. But the broad idea holds. Regions of higher gas density and active star formation appear as arm-like patterns, and the sun's orbit carries it through different environments over time. Passing through a denser region can mean more molecular clouds nearby. It can mean more young, massive stars. And massive stars, while they are rare, have outsized influence because they end as supernovae. Supernovae enrich the interstellar medium with heavier elements and can trigger further star formation, but they also produce energetic radiation and shock waves over long times. Some researchers have wondered whether the sun's passage through different galactic environments might correlate with changes in impact rates or subtle shifts in cosmic ray flux that could influence climate. The evidence is complex and not decisive, but the possibility itself highlights a truth. The galaxy is not just a backdrop, it is a dynamic setting. There is another structure tied to our location that is worth holding in the mind tonight because it brings the cosmic scale close without becoming harsh. Far beyond Neptune, there is a distant reservoir of icy bodies often called the Oort cloud, a vast, loosely bound shell of remnants from the solar system's formation. These objects are held by the sun's gravity, but only weakly. Over time, gentle gravitational nudges from passing stars, from the broader tidal field of the galaxy, or from the influence of massive molecular clouds can perturb some of these distant bodies. A fraction of them may fall inward, becoming long-period comets that visit the inner solar system after spending millions of years in the deep dark. Again, this is not a nightly fear. It is not a reason to tighten your mind. It is simply another reminder that the solar system is not sealed. It is connected lightly to the galaxy's motions. And our local region, the Orion Arm, offers something else that is quietly remarkable. It contains the traces of recent star formation, close enough that the sky we see is partly shaped by it. Many of the bright stars in the night sky are relatively nearby, on the scale of a few hundred light years, and some belong to loose associations of young stars that formed in the last few tens of millions of years. These associations, along with their supernovae, likely contributed to shaping the local bubble itself. In other words, the hollow we are traveling through may be partly the result of nearby stars that lived and died while early humans were still far in the future, and while Earth's continents were in different configurations than they are now. If you imagine the local bubble as a cavity, you can also imagine its boundaries as bright in certain wavelengths, because denser clouds and dust sit there, illuminated by surrounding stars and shaped by ancient shock waves, Some recent studies suggest that the Sun may have entered the local bubble a few million years ago, though the exact timing depends on models of its motion and the bubble's evolving shape. Even that uncertainty is part of science's quiet honesty. We refine, we update, we adjust. We do not demand a perfect story before we allow ourselves to rest. Rest does not require certainty. It requires gentleness. So we keep moving through our neighborhood in this gentle way, noticing how the Orion Arm is both ordinary and extraordinary. Ordinary because it is one segment among many in a galaxy of hundreds of billions of stars. Extraordinary because it is our segment, the place where the Sun has spent enough time in relative stability for life to emerge and persist. This is sometimes framed as a question of habitability on a galactic scale. Not just whether a planet is the right distance from its star, but whether the broader environment is stable enough over billions of years. Too close to the galactic center, and the density of stars increases, along with the frequency of energetic events. Too far out, and the abundance of heavier elements can be lower, making it harder to form rocky planets like Earth. The Sun's location in the disk, in a moderate density region, has often been described as a kind of quiet compromise. It is not a guarantee, it is not destiny. It is simply a set of conditions that, over long time, has allowed complexity to unfold. If your mind wants to turn that into a sharp thought, you can soften it. You can let it become a feeling instead. The feeling of being placed inside a stable lane of a turning galaxy, held by a balance of forces that do not need your attention to do their work. And now, because you have drifted far and returned close again, there is a natural next step, the question of how we know these things with such detail, given that we cannot step outside the Milky Way to look back at it. We can know because we measure motion, we measure light, we measure tiny shifts in position and spectrum and timing. We learn to read faint signals across vast distances. We build instruments that extend our senses beyond the narrow band of visible light. We build surveys that watch the sky repeatedly and patiently, gathering data that only becomes meaningful when it is combined and compared. In our local region, these measurements become especially powerful because we can see many nearby stars clearly and track their motions with precision. We can map how groups of stars move together, revealing their shared origins. We can trace the three-dimensional structure of dust that hides the inner galaxy from view. We can measure the flow of gas in the disk using radio observations of neutral hydrogen, including the 21-centimeter emission line that has been so important in mapping galactic rotation. We can observe warm dust in infrared. We can detect hot plasma in X-rays, and we can combine all of it into a layered portrait where the Milky Way is not a single picture, but many overlapping ones, each revealing a different component of the same reality. The Orion Arm, the local bubble, and the Sun's orbit are not just poetic ideas. They are inferences grounded in these measurements, refined by better instruments, and checked against models that must match what the sky actually does. And there is something calm about that method if you let it be calm. Science at its best is not a rush. It is patient attention. So as we continue, we can let the neighborhood remain with us, not as a list of facts, but as a quiet setting, a star moving through a warm cavity of interstellar gas passing slowly through clouds, bobbing gently above and below the galactic plane, carried along in a broad orbit that takes hundreds of millions of years. And from that setting, we can begin to follow the tools that made it visible. The star catalogs, the all-sky surveys, the multi-wavelength maps, the techniques that stitch faint signals into coherent structure. The way a map is built, not by one dramatic discovery, but by a long accumulation of careful measurements until the hidden geometry of the Milky Way begins to come into focus like a landscape emerging at dawn. So we will keep the pace gentle as we move forward from the lived-in corner of the Orion Arm into the quiet work of observation, where the galaxy reveals itself, not all at once, but gradually, through a billion tiny data points that together become a kind of calm knowledge. We can stay close to that quiet neighborhood for a moment, not because it is the most dramatic region of the galaxy, but because it is familiar enough to feel steady. In the Orion Arm, between larger spiral structures, the Milky Way does not press in on us. The sky, when it is dark enough, still has room to breathe. And from this steadier place, a different thread begins to glow. Not only where we are, but how we learn what we are inside. Most of the galaxy is hidden from ordinary sight. Dust gathers in long lanes, and in the visible band it can look like absence, like the galaxy has gaps where it should have light. But the dust is not a hole, it is a veil, and veils can be read if you learn to listen with more than one kind of light. There is a calm idea beneath this. The universe is not quiet because it is empty. It is quiet because it is vast, and because most of its messages arrive gently, spread across wavelengths that do not shout. In visible light, you see the bright points, the star fields, the sharp edges where darkness cuts through the disk. In infrared, the same direction becomes softer and deeper, as if the galaxy is warming from within. Infrared light slips through dust more easily, revealing crowded regions where stars are being born, and the glow of older stars packed into the central bulge. The same sky, a different layer. In radio, the galaxy becomes even stranger and more spacious. Cold gas that is invisible to the eye can announce itself there, not as a picture you would hang on a wall, but as a structure you can trace. Vast clouds, long filaments, and slow-moving reservoirs that drift between the arms. You begin to sense that the Milky Way is not only stars, it is also a medium, a weathered ocean of gas and dust and magnetic fields, threaded by gravity. In X-rays, the scene changes again. You find heat where you did not expect it, plasma at millions of degrees, expanding shells from old explosions, and compact objects that draw matter inward until it shines with fierce intensity. These are not places you would want to be, but they are also part of the galaxy's balance. They stir the medium, enrich it, carve bubbles, and then fade. And in gamma rays, the highest energy light, the Milky Way can reveal vast structures that feel almost like ghosts, not because they are unreal, but because they are difficult to see from inside. Enormous lobes above and below the disk, faint outlines of ancient activity near the center, signals that tell you the galaxy has moods that unfold over millions of years. All of this might sound like complexity, but notice what it does when you hold it softly. It turns confusion into layering. It turns darkness into information. It suggests that the galaxy is not refusing to be known. It is simply asking for patience and for instruments that match the scale of what they are trying to read. And so, over the last century, astronomy has become a kind of gentle accumulation. Not one revelation that changes everything in a single night, but a slow gathering of clues that, together, sharpen the picture. One of the most important of those gatherings has come from a spacecraft that does something deceptively simple. It watches, it measures, it repeats. The Gaia mission, operated by the European Space Agency, has been scanning the sky again and again, building a catalog of more than 1 billion stars. Not only where they appear on the sky, but how they shift over time. A star is not a fixed pin. It moves. It carries a history in its motion and in the subtle way its light changes. Gaia measures distances through parallax, the tiny change in a star's apparent position as Earth moves around the sun. It measures proper motion, the slow drift of stars across the sky. For many stars, it also measures their speed toward or away from us. And it does all of this with a precision that can feel unreal when you translate it into human terms, as if you were tracking the movement of a coin from thousands of kilometers away. But you do not need the technical weight of it. You can keep the image instead. 1 billion points, each one measured many times. 1 billion quiet notes in a long, patient song. When those measurements are placed together, something happens. The Milky Way stops being only an impression. It becomes a map. Not a perfect map, not a finished one, but a living one. Streams of stars emerge, long and pale, stretched out like tidal scars. These are the remnants of smaller galaxies that wandered too close long ago, were pulled apart, and then folded into the halo. Their stars still travel together loosely, sharing a common origin, even as they wrap around the Milky Way in arcs that take hundreds of thousands of years to complete. Clusters appear as families, not only in space but in age and composition. Some groups of stars share the same chemical fingerprints, the same mixture of elements forged in earlier generations of supernovae. This is one of the quiet miracles of spectroscopy, that light can carry a record of what a star is made of, and therefore a clue to where and when it formed. With Gaia's motions, and with spectra from ground-based surveys that measure stellar chemistry, astronomers can do something that feels like archaeology. They can separate populations. They can identify stars that were born in the Milky Way's early disk and stars that arrived later as part of an accreted system. They can read the thick disk and the halo as if they were layers in sediment, each one preserving a different era. And the galaxy itself begins to show that it is not smooth. The disk contains ripples, it contains waves. Stars above and below the midplane do not distribute themselves perfectly. Their motions can align into patterns that hint at a disturbance, a passage, a gravitational tug that happened in the recent past on cosmic timescales, a dwarf galaxy crossing the disk, a massive satellite pulling on the halo, the Milky Way responding not violently but coherently, like a great instrument vibrating after a single low note is struck. This is where the calm pace matters, because it is easy to make this feel frantic, as if the galaxy is a battlefield. But what Gaia shows is not chaos, it is structure. It is cause and effect stretched across time. A gentle physics that leaves signatures you can still measure long after the event itself has faded. and Gaia is only one part of the way we see. Multi-wavelength astronomy is like learning to touch a sculpture in the dark with different gloves. One glove is sensitive to heat, another to texture, another to motion, another to faint edges. Each one gives you partial truth. Together, they give you shape. Infrared surveys have traced the central bar and the bulge, where dust would otherwise hide the crowded heart. Radio observations map cold gas that will become future stars and also reveal how magnetic fields thread through the medium. X-ray telescopes follow the hottest regions, supernova remnants and compact objects, where matter becomes plasma and energy becomes visible. Gamma-ray instruments reveal large, faint structures that tell of activity on scales the eye could never guess. And through all of this, the Milky Way becomes less like a single photograph and more like a layered atlas. A galaxy you can read the way you read weather patterns, geology, and ocean currents, not by looking once, but by observing over time. There is also another tool that does not observe the galaxy directly, but recreates it. Simulation, not as fantasy, but as physics applied to a vast system. In these simulations, gravity pulls matter into filaments, gas cools and collapses, stars form and die. Supernovae stir the medium. Dark matter provides the underlying scaffold. Satellite galaxies fall in, are stripped, and leave streams behind. When the inputs are close enough to reality, the outputs begin to resemble the Milky Way we infer from observation. Spiral arms, bars, thick disks, halos, warps, ripples. Not identical, because no simulation is perfect, and the initial conditions of our own galaxy's history are not fully known, but similar enough to let scientists test hypotheses, to see which histories produce structures like the ones we actually measure. This is another calm idea. The Milky Way is not only something we look at, it is something we can model, replay, and constrain. We can ask gently what kind of past would lead to this present. And then there is the place where our desire to see becomes almost paradoxical. The center. Sagittarius A is hidden behind dust, invisible light, yet the environment around it is luminous in radio, infrared, and X-rays. Gas swirls, stars race, flares appear and fade. And for decades, astronomers watch those stars in infrared, tracing their orbits, letting simple celestial mechanics point to the presence of a compact mass of about 4 million suns. It is one thing to infer a black hole. It is another to glimpse its shadow. The event horizon. Telescope is a worldwide network of radio observatories that combine their data to act like one instrument the size of Earth. They observe at very short radio wavelengths, where the resolution can become sharp enough to image the bright region close to a black hole, where gravity bends light into a ring-like glow. The resulting images are not casual snapshots. They are reconstructions built from sparse measurements, stitched together by careful algorithms, tested against many possible solutions. But still, what emerges is remarkable. A bright ring and a dark center, a silhouette where the event horizon lies, a visible sign of a place where space and time are strongly curved. You do not have to push your mind into the math of it. You can keep the softer truth. It is possible to measure something that cannot be seen directly. It is possible to infer shape from absence. It is possible for a planet of radio dishes spread across continents to agree on the outline of a shadow in the center of a galaxy. And if you are listening in the dark, half resting, that idea can feel strangely tender. Not because it is small, but because it is precise. Because it suggests that knowledge can be made without force. Even the most extreme gravity we know, can be approached with patience and quiet attention. And there is more quiet work underway. Surveys that measure the faint reddening of starlight by dust, allowing three-dimensional maps of the dust itself. Surveys that detect variable stars, whose brightness changes in regular ways that can be used as distance markers across the galaxy. Surveys that trace the distribution of star-forming regions, not only where stars are now, but where they are being born. Surveys that follow the motions of satellite galaxies, using them like test particles to probe the dark halo's shape. Each survey adds a layer. Each layer reduces the need for guesswork. And none of it arrives all at once. It arrives the way sleep arrives, when it is healthy, slowly, quietly, through accumulation, a billion data points, a faint spectrum, a patient scan repeated for years, an archive that grows until patterns begin to reveal themselves, not because someone demanded them, but because the universe was leaving them there the whole time. And as these patterns sharpen, the Milky Way becomes not only a home, but a context, a place with an origin story you can trace, a structure that is still evolving, a system that carries both violence and calm, but mostly calm, because time is long and most processes are slow. From here, the next step is natural. Once you have a map of stars, you begin to notice where those stars are likely to host worlds. Once you have spectra, you begin to wonder what those worlds might be made of. Once you have a sense of the galaxy's neighborhoods, you begin to ask which neighborhoods are gentler, which are more stable, which might allow a planet to keep its atmosphere, keep its oceans, keep its long, uninterrupted stretches of time. So we will keep the pace steady as we move on, letting this careful work of observation become a soft background, and letting our attention drift toward the quieter question that follows almost automatically, like a thought that forms on its own. In a galaxy with hundreds of billions of stars, how many of those stars have planets, and how many of those planets have the kind of calm, long-lived conditions where life could persist quietly for billions of years? When the Milky Way is mapped with patience, a quieter truth appears. The galaxy is not only a place of dazzling events, but also a set of long conditions. Temperature ranges, radiation backgrounds, distances between stars, the slow availability of elements heavier than hydrogen and helium, made inside stars and returned to space. The steadiness of an orbit that can remain unbroken for hundreds of millions of years. And when you begin to think in conditions rather than in headlines, the question changes. It becomes less about whether the universe is dramatic and more about whether the universe is habitable. Not everywhere in the Milky Way offers the same kind of calm. Closer to the center, stars are packed more tightly. There is more dust, more gas, more frequent star formation, and more energetic activity. In such regions, supernova explosions may be more common, and the background radiation can be harsher. Farther out, the disk thins. Stars are more widely spaced, and catastrophic events may be rarer, but the raw material for building rocky planets can also be less abundant. because the elements that make rocks, oceans, and atmospheres are not primordial, they are recycled. They are the ash and breath of earlier generations of stars. This is one reason astronomers sometimes speak of a broad idea called the galactic habitable zone. It is not a sharp ring drawn with a ruler. It is more like a gentle preference, a region where the galaxy has had enough time to enrich itself, where heavy elements are common enough to form solid worlds, and where the rate of disruptive events is not too high for long stretches of stability. In this picture, our sun's neighborhood makes a kind of sense. Not perfect, not guaranteed, but plausible. We are not near the crowded center. We are not at the sparse edge. We are in a part of the disk where the sky can remain relatively steady for a long time, where stars are spaced far enough apart that their gravitational influence is usually mild, and where a planet can keep an atmosphere without being constantly stripped by intense radiation from nearby catastrophic events. You do not need to hold this as a comforting story. It is simply a way of seeing the galaxy as a gradient of environments, some gentler, some harsher, some noisy, some quiet. And once you begin to see the Milky Way as a landscape of environments, another realization follows naturally. There are worlds everywhere. For most of human history, planets were a local secret. We knew only the few that shared our sun. Even in the last century, it was still possible to imagine that planetary systems might be rare. Now we know they are common. The sky is full of them. Stars with close, hot giants. Stars with chains of small worlds. Stars with planets on tilted orbits, or planets caught in resonant dances that repeat with steady precision. We learned this not by seeing most of those worlds directly, but by noticing what they do to their stars. Sometimes a planet passes in front of its star from our point of view. The star's light dims by a small amount, and the dimming repeats in a rhythm. This is called the transit method. It is an elegant idea because it turns time into a measurement. A shallow dip, repeating again and again, can reveal the planet's size, its orbital period, and with additional information, a clue to its density. The Kepler Space Telescope made this method famous on a grand scale, staring at a single field of stars for years, looking for tiny repeated shadows. Later, the Transiting Exoplanet Survey satellite expanded the search across much of the sky, focusing on brighter, nearer stars that are easier to study in detail. The details differ, the catalogs grow, but the message is consistent. Planets are not rare exceptions. They are a standard outcome of star formation. Another method listens for the gentle pull of a planet on its star. As a planet orbits, it tugs. The star wobbles slightly. That wobble changes the star's spectrum through a subtle shift in its light, a shift that can be measured with careful instruments. This is called the radial velocity method. It tends to find heavier planets more easily, and it provides something the transit method cannot always give on its own, a better estimate of a planet's mass. When the two methods work together, the picture becomes richer. Size and mass together can suggest composition. A small planet with a high density is likely rocky. A larger planet with a lower density may hold a thick envelope of gas. Between these lies a family of worlds that our own solar system does not display clearly. Super-Earths and mini-Neptunes. Planets larger than Earth but smaller than Neptune, sometimes rocky with thick atmospheres, sometimes more like scaled-down gas worlds, sometimes something stranger that still resists tidy categories. And then there are worlds that stretch the imagination in quieter ways, planets that orbit two stars, where the sky would hold two suns moving in a slow, repeating geometry. Planets with years that last only a few days, racing so close to their stars that their surfaces may be lava. Planets with seasons driven not only by tilt, but by eccentric orbits that bring them alternately close and far, warming and cooling in long arcs of time. Planets that may be covered entirely by deep global oceans. Planets that may have no star at all, drifting through interstellar space, warmed faintly by internal heat rather than by sunlight. The more we learn, the more the galaxy feels less like a single home and more like an archipelago, a scattered chain of possible shores. And because your mind is here to rest, we will not rush. We will let the idea settle. In a galaxy with hundreds of billions of stars, if planets are common, then the number of planets is vast beyond comfortable counting. Even if only a small fraction are rocky, and only a small fraction of those orbit within a temperate range, the remaining number could still be enormous. But the temperate range itself is also more subtle than people often assume. Around any star, there is a region where a planet could, in principle, have liquid water on its surface if it has the right atmosphere and pressure. This region is often called the habitable zone. It depends on the star's brightness and temperature. A brighter star pushes the habitable zone farther out. A dimmer star keeps it close in. This brings us to the most common stars in the Milky Way, red dwarfs. Red dwarfs are smaller and cooler than the Sun. Because they are cooler, their habitable zones lie much closer in. That makes their planets easier to detect with transits. Because a small planet blocks a larger fraction of a small star's light, and because close orbits repeat quickly, giving many chances to see a pattern. Red dwarfs are also long-lived. A red dwarf can burn quietly for tens of billions of years, longer than the current age of the universe. That timescale can feel almost soothing. It suggests that if a planet can remain stable around such a star, it may have a vast span of time available for chemistry to explore complexity. But red dwarfs have another side. Especially when they are young, they can be active. They can flare, releasing bursts of energetic radiation. And because their habitable zones are close in, planets in those zones may be exposed to those flares more directly. There are questions about whether atmospheres can survive, and if they survive, what kinds of atmospheres can endure. There are questions about whether close-in planets become tidally locked, always showing the same face to their star, holding a permanent day side and night side, and if so, whether winds and oceans can move heat around enough to keep a stable climate. None of these questions are settled in a simple way. This is part of what makes the topic gentle rather than exhausting. It is not a single answer. It is a landscape of possibilities. We have reached a point in science where the most interesting discoveries are often not proclamations but constraints. Not, this is what is there, but this is what could be there, given what we can measure. And now we come to one of the most delicate measurements of all, the study of exoplanet atmospheres. When a planet transits its star, a small fraction of starlight filters through the planet's atmosphere before reaching our instruments. Molecules in that atmosphere absorb light at specific wavelengths. The resulting pattern, spread out as a spectrum, can reveal the presence of certain gases. This is difficult work. The signal is small, the starlight is bright, the planet is faint, the atmosphere is a thin shell, but careful observations, repeated many times, can accumulate clarity. The James Webb Space Telescope is designed to make these kinds of measurements with greater sensitivity than many earlier instruments, especially in infrared wavelengths, where many molecules leave strong signatures. Other telescopes, both in space and on the ground, add their own strengths. Extremely large ground-based telescopes, with mirrors measured in tens of meters, will sharpen the view further, separating faint planetary signals from the glare of their stars with increasing skill. What can we look for? We can look for water vapor, carbon dioxide, methane, carbon monoxide, ammonia, sometimes haze, sometimes clouds, sometimes the absence of expected gases, which can be as informative as their presence. We can look for atmospheres that are puffy and hydrogen-rich, and atmospheres that are heavier and more compact. We can look for patterns that suggest chemical disequilibrium, combinations of gases that are hard to maintain together unless there is a continual source replenishing them. On Earth, for example, oxygen and methane together are a kind of chemical tension. Oxygen tends to destroy methane. Methane tends to be removed in an oxygen-rich environment. The fact that both persist implies active processes that keep supplying them. Much of that supply on Earth is biological, but we should be careful. For distant planets, nothing is straightforward. Nature can produce gases in more than one way. Volcanoes can release methane. Ultraviolet light can split molecules and create oxygen in certain scenarios. A planet's history matters. Its star's spectrum matters. Its oceans, if it has them, matter. Its interior chemistry matters. So the idea of a biosignature must be held with humility. A biosignature, if it is ever found, will not be one gas shouted as a final proof. It will be a pattern, a context, a collection of clues that align gradually like the slow assembly of the Milky Way's own map. And yet, even with that humility, the search matters. Because it focuses our attention on something deeply human, even in a cosmic setting, the question of companionship. Here is where the silence enters. If the Milky Way holds so many stars and so many planets, it seems reasonable to imagine that life could arise elsewhere, and if life can arise, it may have more than one path toward complexity. And if complexity can arise, it may have more than one path toward intelligence, technology, and communication. But when we look, we do not see clear evidence of other civilizations. We do not see unmistakable signals in the sky. We do not see obvious engineering on stellar scales. We do not see a galaxy filled with loud technological beacons. This tension is often called the Fermi paradox. It is not a paradox in the sense of a logical contradiction that must be resolved immediately. It is more like a quiet mismatch between two impressions. The impression that the galaxy is large and old enough for many civilizations to have existed, and the impression that the sky so far feels silent. There are many possible reasons, and most of them do not require drama. It could be that the origin of life itself is rare, not impossible, but rare. It could be that simple life is common, but complex life is rare. It could be that intelligence arises but does not often produce technologies that broadcast into space. It could be that technological phases are brief, a few centuries of radio brightness, then a shift to quieter methods that are hard to detect, or a turn inward, or a collapse, or a gentle fading. It could also be that we have not been listening long enough. Modern radio astronomy is young. Our own strongest radio leakage has been traveling outward for only about a century, forming a thin, expanding bubble around Earth. In cosmic terms, that is nothing. Our listening projects, even when they are careful and sustained, cover only a tiny portion of the possible frequencies, signal patterns, and sky directions that could carry an artificial transmission. And it could be that the galaxy is not designed for easy contact. Distances are large. Light is slow. Even a signal traveling at the speed of light takes years to cross the nearest interstellar gaps, and tens of thousands of years to cross the disk. A civilization could rise and fall on one side of the Milky Way without ever overlapping in time with another civilization's receptive phase elsewhere. When you hold the Milky Way in your mind as a slow system, measured in millions and billions of years, the silence can feel less like a mystery that demands an answer tonight and more like a natural outcome of scale. The sky may be full of life and still feel quiet, or the sky may be mostly empty of life and we may be rare. Both possibilities are strange. Both are worth contemplating. Neither needs to be turned into a sharp thought that keeps you awake. So we let it stay gentle. We let the question become part of the background, like a distant star field, present but not pressing. And there is another layer to this, one that makes the topic feel less abstract and more grounded in the galaxy's structure. If life depends on long stability, then not all regions of the Milky Way are equally friendly to it. A planet too close to the center may endure higher radiation backgrounds and more frequent disruptive events. A planet too far out may form with fewer heavy elements available, making rocky worlds less common. Regions near frequent massive star formation may experience more supernova explosions. Regions with crowded stellar neighborhoods may experience more close stellar passes that disturb distant comet reservoirs, potentially increasing the rate of impacts over long spans of time. This is part of the reason the galactic habitable zone is a useful concept. Not as a strict boundary, but as a way to connect the biology question to the galaxy map. It ties the search for life to the same kinds of structures we have already been drifting through: spiral arms, star-forming regions, interarm spaces, halos, and the slow orbit of the Sun. Even the Sun's own path through the Milky Way could matter, not because it is dramatic, but because it is persistent. Over hundreds of millions of years, the solar system may pass through or near spiral arms. It may pass near regions with more molecular clouds. It may pass through regions with different cosmic ray backgrounds. It may experience more or fewer nearby supernova events. The effects on Earth, if any, would likely be subtle, filtered through atmosphere and magnetosphere and geology. But the principle remains. Life on a planet is not isolated from the galaxy that holds it. It is nested. Nested is a good word for tonight. You are nested inside a room, inside a city, inside a planet, inside a solar system, inside a spiral arm, inside a galaxy, inside a local group of galaxies, inside a web of structure that extends farther than the mind can comfortably picture. And because you are nested, you are also protected in certain ways. The interstellar medium around the Sun is not a vacuum, but it is thin. The heliosphere offers partial shielding. Earth's magnetic field deflects many charged particles. The atmosphere absorbs much of the most harmful radiation. None of these are perfect, but together they create an environment where life can persist long enough to evolve complexity. If you allow your mind to rest on that, it can feel quietly astonishing. Not as a triumph, not as a sentimental story, just as a fact of physics and time and chance. That matter arranged itself into a world that could hold water on its surface for billions of years. And now, in this era, we are learning how to ask whether that has happened elsewhere. The search is still early. The first wave has been discovery, finding planets and counting them. The next wave is characterization, learning what those planets are like, what their atmospheres contain, how their climates might behave. Beyond that lies a harder wave, looking for signatures that are not only chemical but contextual, signatures that sit inside a coherent story of geology, starlight, and atmospheric chemistry. This is why the future of the field does not depend on one telescope alone. It depends on ensembles, on surveys that find targets, on follow-up instruments that measure masses, on spectrographs that study atmospheres, on models that interpret those spectra in the context of planetary evolution, on laboratory measurements of molecular absorption and chemical reactions, on patience. If that word feels familiar, it is because it matches the way we began mapping the Milky Way itself. We do not learn the galaxy in one glance. We learn it by returning again and again, letting small measurements accumulate into a map. And somewhere in that growing map, the quiet question of, are there other minds, remains present, not as an urgent demand, but as a long horizon. There is also a second kind of future that sometimes enters people's thoughts here, and it is worth touching with a light hand. The future of travel. With chemical rockets, the nearest stars remain unimaginably far. Even the closest system, Alpha Centauri, is more than 4 light years away. At the speeds of today's spacecraft, a journey would take thousands to tens of thousands of years. But ideas exist that could, in principle, shorten that timescale. Light sails pushed by powerful lasers, fusion propulsion, advanced concepts that remain experimental and uncertain. We do not need those ideas to be real tonight. It is enough to recognize that the human mind naturally extends outward. Once it knows there are other worlds, it wonders about reaching them. But even if no starship ever leaves the solar system, the act of looking already changes the relationship. When you know that planets are common, when you know that the galaxy is full of worlds, the night sky becomes more intimate, not smaller, but more inhabited, in potential. Each star becomes not only a light, but a system. Each system becomes not only a point, but a set of paths and seasons and climates and histories. And here the calm returns, because the scale remains slow. Whatever happens, it happens over long spans of time. Orbits repeat, stars evolve, galaxies merge, the universe expands. You do not need to run alongside that pace. You can simply float within it. So we will hold the main thread of this part as a gentle chain. The Milky Way contains many environments. Those environments influence the stability of planets. Planets are common. Some planets may be temperate. Temperate is not the same as inhabited, but it is a start. Atmospheres can be studied slowly through light. Light carries clues. Clues accumulate into understanding. And understanding opens questions that do not have to be answered tonight. If you've been listening for a while, you may notice that the mind can treat even the largest questions as soft, as long as we do not sharpen them into demands. The question of life elsewhere can be a lullaby when it is presented as possibility rather than urgency. And now, as we continue, there is another future that belongs to our own system, not just to our curiosity. A future written into stellar evolution, into orbital mechanics, into the long dynamics of the local group. The sun is not eternal in its current state. The Milky Way is not eternal in its current shape. The local web of galaxies is not eternal in its current arrangement. These are not threats. They are trajectories, slow ones. So in the next stretch of our journey, we can let the focus shift again from the question of other worlds back to the long story of our own star, our own galaxy, and the immense structures beyond it, the kind of structures that move so slowly that they feel almost still, even as they reshape the night over billions of years. And if you are close to sleep, you do not need to follow every turn. You can let the ideas drift past like faint starlight, the galaxy turning, the disk breathing with slow cycles of star birth and star death, the possibility of countless worlds, the quiet silence between them. And beyond all of that, time, wide and unhurried, carrying everything forward without strain. We can let the question stay open, the way a quiet door can remain slightly ajar without making the room feel cold. If there are other minds out there, they may be separated from us by distance, by time, by choices we cannot guess. If there are none, then this one small world has carried something rare for a while. Either way, the night does not demand an answer. The search can continue without urgency, and the sky can remain gentle. So instead of pushing further into what we cannot yet confirm, we can follow what the universe does confirm, again and again with patient consistency. Stars change slowly. Galaxies reshape slowly. Large structures flow along gravity's long gradients slowly. Nothing snaps, nothing rushes. The future arrives like dawn, not like an alarm. And the closest future written into our own sky is not far across the Milky Way. It is here inside the sun itself. Right now, the sun is in a stable phase of its life. Deep in its core, hydrogen is being fused into helium. That process releases energy, and the pressure of that energy holds the star up against gravity. It is a balance that has lasted for billions of years. It feels steady because on human timescales, it is steady. Still, even steady things drift. Over time, as helium builds up in the core, the sun's internal structure changes. The core slowly contracts and warms. The outer layers respond. The total brightness of the sun increases very gradually as it ages. Some models describe it as rising by roughly about 10% per billion years, not as a sudden jump, but as a slow trend, almost like the turning of a dimmer that nobody touches. If you hold that detail lightly, it can settle into the background. It is not a threat. It is simply a timeline. Earth has lived through immense changes already. Continents have moved. Oceans have opened and closed. Life has adapted to new climates and new skies. The sun's slow brightening is part of that same long story. Far in the distance, in roughly 5 billion years, the sun's main sequence life will end. The core will have used most of its hydrogen. The balance will shift. The core will contract more strongly and heat further while the outer layers expand outward. The sun will become a red giant. A red giant is not a different kind of star as much as a different chapter in the same star. The surface becomes cooler, so the color shifts toward red and gold. The radius grows enormously, so the star fills a larger region of space. The light becomes broader, more diffuse, more enveloping. From very far away, the scene would be calm and luminous. From nearby, it would be transformative. Mercury and Venus are expected to be lost inside the expanded atmosphere of the sun. Earth's fate is more complicated because it depends on how the sun loses mass and how Earth's orbit changes in response. But the deeper point does not depend on the final detail. Long before any possible engulfment, Earth would become too hot for the familiar chemistry of oceans and air. The surface would be reshaped. The world you know would not remain. Even that can be held without tension if the mind remembers the scale of time. 1 billion years is long enough for the very idea of near and far to soften. Events do not arrive like footsteps behind you. They arrive like a slow shift in the angle of light across a landscape. And then the red giant chapter will end. The sun will shed its outer layers into space. Those layers will expand outward as a glowing shell of gas lit from within. Astronomers call this a planetary nebula, a historical name that does not mean planets are involved, only that early telescopes saw rounded shapes and borrowed familiar language. What remains at the center will be the sun's exposed core, a white dwarf. A white dwarf is small, dense, and initially very hot. It no longer generates energy through fusion. It shines by releasing stored heat, slowly cooling over vast spans of time. It becomes, in a sense, an ember left behind. After a long fire, a quiet remnant. There is something strangely soothing about this. If the mind is allowed to interpret it as continuity rather than loss, the universe recycles. Stars enrich the gas between stars. That gas becomes new stars. The heavy elements forged in stellar interiors become the raw material for rocks, oceans, and living bodies. The sun's future is not an exception. It is part of a cycle. And while the sun follows its own slow evolution, the Milky Way does not hold its shape forever either. In the same distant era, another long story will be unfolding. The approach of Andromeda. Andromeda is the nearest large spiral galaxy to our own, about 2.5 million light years away. Measurements show it is moving toward us at roughly 110 kilometers per second. That sounds fast when it is said in a single breath, but over cosmic distances it becomes a gradual drift, like two distant ships that take ages to close the gap. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to begin a close interaction that leads to a merger. This is not a single collision. It is a drawn-out encounter, lasting billions of years, as the galaxies pass through each other, distort, swing apart, and return, again and again, until the separate structures fade into a single larger system. The word merger can sound violent, but for individual stars it is mostly gentle. Stars are tiny compared to the distances between them. Even in dense regions, direct star-to-star collisions are exceedingly rare. The change is gravitational. The overall field reshapes, and the orbits of stars adjust to a new, evolving pattern. If you imagine it as a slow rearrangement rather than a crash, it becomes easier to picture without waking up. Arms stretch. Streams of stars are drawn out into long arcs. Gas clouds compress in some regions, triggering periods of star formation, while other regions become quieter. The distinct spiral disks gradually blur and settle into a more rounded structure, likely more elliptical than either galaxy is today. Some simulations give this future remnant a nickname, Milky Way, a name that is not official, just a shorthand for a combined identity. If the solar system still exists by then, its orbit around the galactic center will likely change. It may move farther out, or take on a more elongated path, or drift into a different region of the merged galaxy. The night sky, over countless generations, would slowly transform. Constellations would not shatter in an instant. They would loosen and reform. The way patterns in clouds slowly change while the air remains calm. There is a particular kind of peace in that pace. It is not the peace of permanence. It is the peace of gradualness. And the Milky Way and Andromeda are not alone in their wider neighborhood. They are the largest members of the local group, a small community of galaxies bound together by gravity. Along with them are dozens of smaller dwarf galaxies, some faint and diffuse, some compact, many of them orbiting, interacting, being gently pulled and reshaped. Over time, as the largest members merge, the local group itself may become more consolidated. Smaller galaxies will continue their long orbits, and some may be absorbed into the growing combined system. The local group will drift toward a quieter state, with less separate structure and more shared gravity. Now, let the view widen again, not quickly, just enough to feel the next layer. The local group sits within a much larger pattern in the universe. Galaxies gathered in clusters, clusters linked by filaments, filaments outlining enormous voids. This is the cosmic web. It is not a rigid lattice. It is a flowing structure shaped by gravity and the distribution of matter after the early universe cooled and expanded. Our region of this web has been described using a name that sounds like a place, even though it is really a basin of motion, Laniakea. It is not a sharply bordered object. It is a region defined by how galaxies move, by the direction their velocities point, like water in a watershed. The scale is immense, spanning hundreds of millions of light years. When the mind holds a structure that large, it can begin to feel like stillness. Not because nothing moves, but because everything moves so slowly that motion becomes more like a background drift than an event. If you want a softer image to carry alongside the facts, you can borrow one from a quieter kind of landscape. Imagine standing on the horizon of a distant world at dusk. The sky is thin and darkening. A pale moon hangs above layers of cloud. The light does not flash. It fades. Shadows lengthen. The surface cools. And the boundary between day and night slides forward like a slow tide. That fading light is a gentle way to picture cosmic change. Not as something that strikes, but as something that arrives by degrees. Or imagine the night side of Earth from orbit again, city lights like warm embers on a curved surface, the atmosphere a thin rim. You are not being asked to interpret it. You are simply being allowed to see it and to feel your thoughts settle into a larger frame. Because this is what the future of the Milky Way does when it is told with patience. It gives the mind space. It says, quietly, time is wide, change is slow, and you do not have to brace yourself against it tonight. If you are close to sleep, the details can remain like soft points of light rather than things to remember. The sun slowly brightening, then swelling, then releasing a shell of gas, a white dwarf cooling, two spiral galaxies drawing closer over billions of years, not colliding like stones but blending like currents, a local community of galaxies settling, a vast web of structure holding everything in place, even as space expands. And with that frame, we can continue forward without any sharp turn. Because the next part does not need to jump away from the Milky Way. It can stay close to home and still feel expansive. From here, we can let our attention move back to the present sky for a moment, to the night we actually live in, and to what it means to see and measure it all. We can drift toward the quiet work that makes these long stories readable. The surveys that trace stellar motion with exquisite precision, the observatories that collect light beyond the visible, the methods that turn tiny shifts into maps and maps into histories. Not as a lesson, not as a list, helps you stay awake. More like a slow, careful unfolding, where each instrument is a way of touching the galaxy without disturbing it, and each measurement is a small, steady step toward clarity. And as that clarity grows, it does not need to become loud in the mind. It can remain gentle like a constellation that becomes easier to recognize the longer you look, without ever demanding that you look harder. So, staying calm, we can let the future remain in the background as a long horizon while the present comes forward again. A galaxy turning quietly, a star drifting through the Orion Arm, and the careful human art of learning, not by forcing the universe to speak, but by listening to the light it has been sending all along, not forward like a sprint, not backward like regret, just onward the way a quiet river keeps moving even when the surface looks still. If you are already close to sleep, you can let the next minutes become softer. You do not have to follow every sentence. You can simply let the images arrive one by one, like distant lights seen through thin cloud. There are certain facts that stay gentle when you hold them the right way, not as homework, but as atmosphere. Earth keeps turning once every 24 hours, a slow, steady habit that never asks permission. The thin rim of air around it stays almost impossibly delicate, yet it holds oceans, weather, and breath. From orbit, the night side is stitched with city lights, and between them are wide, dark regions where the planet rests. That contrast is real, and it is also calming. It reminds the mind that both things can exist at once, presence and quiet, activity and rest. Above that calm turning, the moon keeps its familiar path. Not a spotlight, not a symbol, just a companion of stone and dust, reflecting sunlight in a way that feels like reassurance, a borrowed glow, a gentle proof that even in darkness, light can arrive indirectly, softened, made safe to look at. Beyond the moon, the solar wind keeps flowing outward, shaping a bubble in the interstellar medium. The heliosphere is not a wall. It is a boundary that breathes, responding to pressure and fields outside, adjusting slowly. Even protection in space is not rigid. It flexes. It adapts. If your mind has been trying to be rigid, tonight you can let it learn from that. A boundary can exist without becoming tense. Around our region, there is the local bubble, a low-density cavity about 1,000 light-years across, likely carved by supernovae over the last 10 to 20 million years. That is a long time, and yet it is also recent in the life of the galaxy. It is strange to think that the quietness around us may have been shaped by explosions, and that the aftermath of violence can become a calmer environment. Not because the universe is kind, but because time transforms energy into stillness. That is one of the softer lessons the sky offers. Even the strongest events fade into a gentle background. Our sun keeps its orbit around the Milky Way at roughly 220 kilometers per second, completing a circuit in about 225 to 250 million years, a galactic year. On Earth, we count birthdays and seasons. The galaxy counts in loops that take longer than the rise and fall of entire species. When you remember that, small worries do not become meaningless. They simply stop filling the entire frame. The Milky Way itself is not a fixed picture. It is a barred spiral that is hard to map from the inside because dust hides and perspective overlaps. Yet we have learned to read it anyway, not by forcing it to reveal itself, but by listening across wavelengths. Infrared can peer through dust. Radio can trace neutral hydrogen through the 21-centimeter line. X-rays can reveal hot plasma near supernova remnants and compact objects. The universe speaks in many forms of light, and the mind is capable of learning its dialects. There is dark matter too, the invisible scaffold that helps the galaxy hold together. We do not see it directly, but we see what it does. Outer stars rotate too fast for visible mass alone. Satellite galaxies move as if guided by an unseen gravity. This is not a story about certainty. It is a story about inference, about learning to trust patterns without needing to grasp the entire mechanism in your hands. The mind sometimes heals by doing the same, noticing effects, accepting that not everything has to be visible to be real. Near the center of the Milky Way, Sagittarius A sits with about 4 million times the sun's mass, a supermassive black hole hidden behind dust. We cannot see the event horizon with our eyes, but we can see its influence. Stars close to the center move at thousands of kilometers per second. The Event Horizon Telescope, a global network of radio dishes, has assembled images of black hole shadows, including Sagittarius A, a ring of glowing gas with a dark center, a shadow made from radio waves. That fact is almost impossible, and yet it happened quietly through patience and collaboration. The mind can take comfort from that. Complex things can be approached without force, by steady attention, by many small signals gathered over time. And then there is the long history written into streams. The Milky Way has grown by accreting smaller galaxies. The Sagittarius dwarf has been pulled apart, leaving stellar streams that wrap around our galaxy like faint tidal scars. That is a cosmic way of saying that the past does not disappear. It stretches, it thins, it becomes part of the larger structure. In your own life, the past can do something similar if you allow it. It can remain as a quiet thread, not as a weight. In the far future, Andromeda approaches at roughly 110 kilometers per second, and in about 4 to 5 billion years, the Milky Way and Andromeda will merge. Not like a crash, but like a slow blending of two vast systems, reshaping orbits, drawing out tidal tails, compressing gas, then settling into a new form. The universe does not hurry change. It lets it arrive with time. If your mind has been carrying the fear that everything changes too fast, the galaxies offer another rhythm. Change that takes billions of years still counts as change, and it does not need panic to be real. And beyond these local stories, there is the wider structure, the local group, and the larger flow within the cosmic web, regions described by motion and gravity, immense patterns like Laniakea that span hundreds of millions of light years. In that scale, urgency becomes smaller, not because it is mocked, but because it is placed, like a candle flame seen in a vast, dark field, still important, still warm, just no longer mistaken for the whole night. These facts do not need to be memorized. They can be used the way you use a horizon. You do not carry it in your hands. You simply let it exist, and it changes how the world feels. If you want a slightly different angle now, something a little newer, but still gentle, you can think of attention as a kind of orbit. In the day, attention often spirals tightly around a few points. A message you did not answer, a thought you replay, a mistake you rehearse. The orbit becomes small, fast, repetitive. That is how the mind exhausts itself. Tonight, you are widening the orbit. You are letting your attention move farther out, where the curves are broader and the speed feels slower. The same mind, the same life, but seen from a calmer distance. That does not erase problems. It gives them room to breathe. You can also let the idea of mapping become a quiet metaphor. Gaia measured more than 1 billion stars, not to dominate the sky, but to understand the shape of our home. It took tiny data points and made a structure visible. Your own mind works like that too. When you treat it gently, small moments of clarity, small sensations of safety, small habits repeated, they add up. They do not solve everything at once, but they refine the map. And you can let one more image settle in, simple and slow. Imagine a horizon on a distant planet at dusk. The sun there is lower than ours, or maybe larger, cast in the wide amber glow across ice plains. The light fades gradually, no drama, just a steady dimming. Above, a moon hangs in quiet suspension, and beyond that, a field of stars that does not flicker, only waits, or return to Earth's night side from orbit. The city lights are soft and scattered. The oceans are dark. The atmosphere is a thin rim, barely there, and yet it holds a world, or drift into the Milky Way from far outside. A spiral turning patient over billions of years, dust lanes like soft shadows, a central glow, arms that are not solid lines but regions where stars and gas and time gather into patterns, or drift nearer to our own neighborhood again. A low-density cavity of warm, interstellar gas, a partial shielding bubble shaped by the solar wind, a small star carrying a few worlds through the Orion Arm, quietly, without needing to announce itself. If you are close to sleep, you can let these images become a place rather than a story, not a conclusion, not a cliffhanger, just a quiet region of thought you can float inside. A thin atmospheric rim, a slow turning sphere, a borrowed moonlight glow, a spiral in the dark, a gentle drift through warm, rarefied gas, a horizon where the light fades without hurry, and somewhere in all that space there is a small pocket of calm, a sky that does not demand anything from you. Just a wide, quiet night where it is safe to let your mind loosen its grip and rest.